Maybe we just start now. Oh, before that, can you hear my voice clearly? Yes, okay. So maybe first we'll discuss number 2 or number 3. Which one do you want? Number 2 or number 3? Any request? Number 3, okay. Yeah, number 3 is a bit different, yeah. Number 2 is, yeah, so lah. Number 2, yeah. Number 3 is a bit different. Okay. Now let's look at the screen. Number 3. So here we have it's like annulus, yeah. It's like annulus, but it's horizontal. Yeah, it's like annulus, but it's horizontal. And then the inner cylinder is not can be moved to the right or to the left, but in this case the inner cylinder can be moved to the right. Okay, so in the beginning, in the space between those two cylinders, we have fluid and the fluid is stationary. Yeah, means that the fluid is just stay there. Yeah, and then at one time the steel or the cylinder inside, the small cylinder, moves horizontally to the right at constant velocity v. Okay, so it moves to the right at constant velocity v. Okay, so when the small cylinder moves to the right, the fluid in between those cylinders, which was initially in stationary state, will start to move as well. Yeah, will start to move as well. Okay. Now, the question is first to sketch the fluid velocity profile in the annulus space, starting when the wire moves to the right until it reaches a steady state. Okay, so the key point is when the wire moves to the right until it reaches a steady state. Okay, so you are asked to sketch the fluid velocity profile when it is in the non-steady state or in the unsteady state condition. Okay? And the second, build a shell momentum balance in order to obtain a partial differential equation. Okay, yeah, so. Okay, and at the end, you are asked to state the boundary conditions. Okay. Sekarang kembali ke layar ya. So my first question is, do you understand? Do you understand the case? Do you understand the problem, or do you understand what we're being asked? Okay, do you understand the situation? Do you understand the problem and the phenomena in the problem? Okay. So maybe yes, yeah. Okay, so if I draw, yeah, if I draw the okay, like that. Now, if you are asked to draw the velocity profile, yeah, velocity profile on the fluid in steady state condition, this is velocity and sorry. This is the radius and this is the velocity. Okay. Just say we have this axis R and C. Yeah. So if you are asked to draw the velocity profile in steady state condition, yeah, what you gonna have is something like this, yeah. Or if I draw it here, your velocity looks like that. Okay, but that's in steady state condition. Yeah, so in this case actually pretty similar with what we have when what we have in our first meeting, when we have two parallel plots and then the lower plots is moved to this direction, velocity v, and then initially constant, you will get this velocity profile. Okay, but that's in steady state condition. Yeah, steady state condition. Now the question in question 3 asks you to draw the velocity profile start when the inner cylinder start to move to the right until it reaches steady state. So basically you are asked to draw the unsteady state condition. Okay, so for the unsteady state condition, when you first move the inner cylinder to the right, yeah, when you first move the inner cylinder to the right, the fluid that moves to the right is only the fluid in the surface of the cylinder. Yeah? Okay. The further away the fluid from the cylinder, the velocity reduces. Okay? So basically, it will look like this. Okay? So that's when you first move the inner cylinder to the right. Yeah? The fluid at R equal to 0 here. At R equal to 0 in the center, yeah. Maybe it's not 0, yeah. It's R equal to, what is the inner radius? We don't have inner radius. Just say the inner radius is RK. Yeah. So at R equal to RK, the velocity is the maximum velocity V. Okay. At R equal to, just say the RB, yeah. At R equal to RB, the velocity is 0. Yeah, the velocity is 0 because the outer cylinder is not in motion. Okay. Nah, as the time pass, the fluid in the surface of the inner cylinder will transport the momentum to the fluid adjacent to itself. Okay, so basically the velocity of the fluid will increase. Okay, and finally, at steady state condition, we will have this profile. Okay, any question for that? No question? Okay, now then how to construct the shell momentum balance? Yeah, how to construct the shell momentum balance? So what we have, yeah, what we usually have in at class is that we know momentum in minus momentum out plus the external force. In steady state condition, it equal to 0. Yeah, but that's in steady state condition. In this case, our case is not steady state. Okay, so when we have unsteady state condition, this part is not 0. But let's say this is the rate of accumulation. Yeah, we briefly discussed about this when we learn about the equation of change. Yeah, so basically in this in the right hand side here we have rate of accumulation, but we usually say that this is 0 because we have steady state condition. Yeah, but in this case we have unsteady state condition, so this rate of accumulation is not 0. Yeah, it has a value. The momentum in, yeah, this one is V R Z at R 2P R delta L, okay, minus VRZ at R plus delta R 2VR delta L, okay, plus VZZ at Z 2PR delta R minus VZZ at Z equal to L 2VR delta R. And the external forces, yeah, the external forces, actually the external forces you can write rho G, yeah, rho G 2VR delta R L, okay, rho G, but actually because your case is horizontal, yeah, because your case is horizontal, and for same height you don't have hydrostatic pressure, yeah, you don't have hydrostatic pressure, so basically you can just neglect this one, yeah, okay, this will be equal to, yeah, rate of accumulation, yeah, this is the rate of accumulation, dou over dou T rho V Vz 2 VR delta R L. Yes, this is the momentum concentration, and this is the volume. Okay, maybe question? Don't have question? Okay. So basically this is what we have. Yeah. We can divide everything by 2V delta RL. Okay. We will have VRZ times R divided by delta R plus VZZ 2V times R divided by L equal to dou over dou T rho VZ to VR. Yeah. Okay. Okay. All good? Do I miss something? No, yeah. I think all good. Looks fine. Yeah, looks good. Then, just as usual, we have to define what is VRZ. Yeah, you can do it quickly now. VRZ is only tau RZ. The other component is just 0. Yeah. And the VZZ is sorry. Should have minus here. Yeah, I think we should have minus here. Yeah. Maybe I just fast forward a bit. Yeah. So minus dou R. Yeah. Okay, we have minus because it's from R to R plus delta R. Okay. I hope it's correct. If I'm wrong, correct me, yeah. So the VZZ, we have rho VZ, and we also have pressure actually. Okay. So now I can write minus dou tau RZ R over dou R plus okay, the VZZ in and out, the velocity in and out is similar, yeah, similar. So this term is cancelled out when I put it here. Then the pressure, yeah, the pressure. How about the pressure? How about the pressure? How about the pressure here and here? Do they have pressure differences? Do they have pressure difference? No, yeah, they don't. They don't have pressure difference in and out. Why? Because we have no flow. Yeah, there's no flow. So basically the VZZ is all 0. Okay. Now, what I will have at the end is equal to dou over dou t rho VZ R. Yeah, is that correct? Yes. Okay. Or I can extend it a bit. Dou over dou R times R minus mu dou VZ over dou R. Okay, minus and minus become positive. R mu dou VZ over dou R. You were not asked to solve this equation, yeah. You were not asked to solve this equation. You just need to have this equation and then state what is the boundary condition. So so how many boundary condition you will have? You will have 3, okay? Because you have 3, you're gonna need 3 differentiation. Yeah, so you basically have 3 boundary condition. Okay. One boundary condition is in respect to t, and 2 boundary condition is in respect to r. Yeah, r. Okay, so for the first boundary condition, yeah, at t equal to 0 means that at the beginning of the phenomena, yeah, at t equal to 0, v equal to 0, Vz, yeah, Vz equal to 0, yeah, because nothing moves, yeah, nothing moves everywhere. Second boundary condition, at r equal to rk, yeah, at r equal to rk at the outer of the inner cylinder, Vz is v, okay. And the third boundary condition at r equal to rb, yeah, the big cylinder, Vz equal to 0. Okay, so that's how to solve equation problem number 3. Maybe question, yeah. Okay. Yes, maybe Ataya first, yeah.
Ma'am,
Yes.
I want to ask. I still don't get it how we determine the boundary condition with 1T and 2R.
With what? Sorry.
The boundary
Huh?
condition, why we use 1T and 2R.
Oke, oke. Oke ya. So, saya harus tutup lagi ya. Ah, nggak usah ya, berarti saya ngomong sini ya. Iya, tutup aja deh. Dari sini aja ya. Oke. Oke. So, uh, let's look at this equation ya. This equation says that the change of something over t, ya. The change of something over t. If you have change of something over t, means that your boundary condition should be at t equal to something, ya. Velocity is something, ya. Okay, in this equation you have change of something over t, 1, yeah, and then you have change of something over r, okay, and you also have change of something over r, okay, so that's why you need to have one boundary condition in respect to t and two boundary condition in respect to r. Okay, is that clear, Ataya?
Yes, thank you, ma'am.
Yes. Next question, Zevania. Why tau z doesn't exist? Okay, isn't there a velocity gradient over z-axis since it changed along the pi? Okay. Okay ya. Tau zz is dvz over dz, ya. Dvz over dz. Okay, so dvz over dz means the change of velocity, yeah, the change of velocity. Okay, yeah, maybe I just write it down. The change of vz at different z, yeah, at different z, but at equal r, yeah, and also at equal observation time. Correct? Yeah, dvz over dz is the change of velocity to the z directions at different z. Yeah, so if at z over here, at z over here, at z over here, over here, over here, over here. Yeah, the velocity change at different z, but the observation should be done at similar radius and also at similar time. Yeah, so it's only change over z. Okay. Yes, that's correct that there is a velocity gradient over z-axis. Okay, if you say you have velocity gradient over z-axis, you look at the condition at different observation time, correct? Yeah, if you observe the condition at similar time, at similar observation time, your velocity at similar z will always be the same. Yeah, but if you look at, for example, yeah, okay, so now at t0, I move this pipe. Okay, if you observe the systems at t 1 second, you will have, for example, this profile. Okay, if you observe the system at t2 second, you will have this profile. Okay, this profile is for 3 seconds, This profile is for 4 seconds. And finally, this for 5 seconds. Example, okay? Now, the dv over dz means that you've observed the velocity at similar time. Yeah, at similar time, the velocity at any point at similar at similar r, different z, will always give you a similar number. Yeah, it's different. If you then observe again at t equal to 3 seconds, example, yeah, you will have different Vz. Yeah, so you have the velocity gradient over z if you observe the system at different time. Okay, is that clear? Sorry, is that clear, Zephanie?
Okay, ma'am. Thank you.
Okay, you're welcome. Okay, maybe more question? Saya matikan dulu ya. Do you have more question? Any of you managed to do this correctly yesterday? Any of you? That's fine, yeah. Or this question was made as advanced question. Yeah, this is advanced question. Yeah. So we made two standard question, number 1 and number 2. Yeah, that's standard, and you are expect to be able to solve that question. And this one is the advanced one. Yeah. Okay, that's fine. Okay, maybe now we move to number 2. I think number 2 and number 1, I think that's pretty easy, yeah. Nothing special. Number 3 is special. Did you communicate with the regular class or the Jatinangor class? Any of them can solve the third question? If you have information, because I haven't asked my students in other classes. Okay. Okay, yeah. So for problem number 2, we have annulus. Yeah, okay. So in this exam, everyone loves cylindrical coordinates. Yeah, I don't know why. Okay, we have annulus between two coaxial vertical cylinder filled with Newtonian fluid. Okay, the height of both cylinder is h, the density and viscosity is constant. Inner cylinder rotates clockwise at angular velocity 2 omega, yeah. The outer cylinder rotates counterclockwise at angular velocity omega. Then the fluid inside moves laminarly in the direction of theta. Okay. Yep. Now let's go back to the whiteboard. So we have annulus like this. Yeah. Okay. Annulus like this. And the inner cylinder moves clockwise to this direction. Yeah. This direction to omega, and the outer cylinder moves counterclockwise like this, omega. Yeah. So just like number 3, the fluid in the beginning was stationary, just inside the annulus, but nothing moves. Yeah, nothing flows. Just stay there. Okay. Okay. When you have problems like this, intuitively you will not try to solve this problem by using the momentum balance, shell momentum balance. Yeah, it will be very difficult. So you're gonna solve this equation using equation of change. Yeah, I have explained to you, I have said to you that everything that rotates, we're gonna solve that with equation of change, equation of motions. Yeah, so that's why we learn equation of motions, because things sometimes get complicated. Example, rotation. Yeah. Okay, if you, yeah, you can open bird later, yeah, but I believe you have done that before, yesterday. So in this condition, we have phi theta, yeah, we have phi theta, phi r we don't have, phi z we don't have as well, yeah, so we only have phi theta, yeah. When you put or when you look at the equation in b, is it b5 or b6, yeah. I think you should start from B6. Yeah, you should start from B6. If you put all the non-value, all the non-condition in equation B6, what we will have is 0 equal to minus. So I will write. Yeah, I will write things in the left, in the right hand side, 1 over r dou p over dou theta plus mu dou over dou r 1 over r dou over dou r phi theta plus rho g theta. Okay, yeah. So I want to ask you, yeah, this equation. Okay, I want to ask you, do we have gravitational force to the theta direction? Do we have gravitational force to the theta direction? G theta, do we have G theta? No. Good. No. This one is 0. I will just erase this. Yeah. Now, do we have pressure differences over theta? Do we have change of pressure over theta? Over theta? No. Yeah, no as well. Correct. So what we're gonna have is just this. Yeah, just this. And then we can quickly solve this equation. We can quickly solve this equation. Mu moves here, 0. First integration, C1. Okay. And then we should times r moves here, r equal to dou over dou r phi theta. Okay, next integration, c1 r square over 2 plus c2 equal to r phi theta. Then we have phi theta c1 r divided by 2 plus c2 over r. Yeah, am I correct? Yes. Yeah, so this is our velocity profile equation. Yeah. Now we need two boundary condition. Yeah, two boundary condition. We have 1 and 2 integration constant. The first boundary condition and the second boundary condition. The first boundary condition, yeah. at r equal to rk, the small one, yeah, rk, at r equal to rk, the radius of the small cylinder, the velocity is 2 omega rk. Yeah, at r equal to rb, big cylinder, yeah, the velocity is omega rb. Don't forget to put minus. Yeah, why we need to put minus? Because it rotates at different direction. Yeah, it rotates at different direction. Yeah, just like the last quiz that we have. Sorry, I really provide the what's the kunci jawaban very late, yeah, just h-1. Okay, but in that case we also have different direction uh, of movement, yeah, I think, yeah, we have conveyor belt, yeah. In that answer for the boundary condition, we have velocity plus and velocity minus, this one as well, yeah. So I love to state that clockwise is positive and counterclockwise is negative. But if you want to state oppositely, yeah, this one is negative, this one is positive, that's fine as well. Yeah, as long as one of them is negative and one of them is positive. Okay. Then put all the equation, yeah, put all the boundary condition to this equation. Okay, and finally, yeah, long story short, you will have C1. I will read everything I write here, yeah, so I can write things quickly. 2 times 2 omega rk square minus omega rb square divided by rk square minus rb square. Hopefully it's correct. You can check later. Yeah. C2, we're gonna have 3 omega divided by 1 over rk minus 1 over rb. Forget the square. Okay. Okay, so this is the C1 and C2. Yeah. What was being asked is the torque. I think the torque, yeah. The torque acting on the, sorry, is it the torque? Torque acting on the inner cylinder. Okay, torque inner cylinder. Okay, so the torque acting on the inner cylinder, if you still remember, yeah, torque is F times the lever arm. The force is tau times the surface area times the lever arm. Okay, so how to get the tau? If you use table B5, that will give you r tau equal to constant. Yeah, just like just like our discussion last week. So tau should be obtained from table B1 or B2. B1? Yeah. Tau r theta equal to tau theta r. Yeah. This is minus mu r dou over dou r v theta over r. Okay, so this is the equation for tau r theta. Okay, minus mu r, dou over dou r, phi theta over r. Okay, now phi theta over r. Yeah, phi theta over r is C1 divided by 2 plus C2 over r squared. Okay? Okay, then you just need to put this value here. Tau r theta equal to minus mu r dou over dou r C1 over divided by 2 plus C2 divided by r squared. Yeah, do one differentiation. Yeah, do one differentiation. Basically, C1 over 2, if you differentiate that equation, that will be 0. Yeah, okay. So what you're gonna have is minus mu r, integration of this. What is integration of? Sorry, not integration, differentiation. Minus 2 over r C2 minus minus 2 over r. Okay, C2. I think it's correct, yeah. But negative and negative. Yes, positive. Now we just need to put what is C2. Mu r 2r. What is C2? C2 is 3 omega divided by 1 rk square minus 1 over rv square. Yeah, I think this is tau r theta. Okay, tau r theta, put tau r theta here. The surface area, what is the surface area? 2 phi r k, yeah, small inner cylinder times L, and the lever arm is rk. Yeah, okay, you need to check one thing. This is annulus, yeah. If you still remember our previous meeting, we have annulus. And then we have fluid flowing upwards like this, yeah. And if you still remember, the velocity profile looks like this. We have a maximum value somewhere, and then if you still remember as well, the torque, the tau has positive and negative value. So remember, the tau here at the outer cylinder is positive and here is negative. Yeah. Do you still remember that? Yes? Do they answer yes? Okay, good. Yeah. So similar with this case, but yeah, not similar, just almost similar. If you look at our case from above, here, the inner cylinder moves to this direction, 2 omega. Yeah, the outer cylinder moves to this direction, omega. Okay, at some point, because the movement of the cylinder is at different at opposite direction. At some point over here, yeah, I don't know where, the velocity should be 0. Yeah, so the velocity profile will looks like this. Somewhere, I don't know where, the velocity profile will be 0. Okay, So the velocity profile will look like this. Okay, the velocity is 2 omega rk here, and reduce until it is until the velocity over here is omega rb, but in opposite direction. Okay, in this case you will also need to check whether the tau at the inner cylinder is positive or negative. How to check that? Just similar with the strategy that we use for this case. Look at the velocity gradient. If the velocity gradient is positive, then you will have negative tau. If the velocity gradient is positive and is negative, you will have positive tau. Because tau is minus mu velocity times the velocity gradient. Okay. I hope it's all clear. Number 2 is just like that. And number 1, I believe number 1 is easy peasy for you. Number 1 is easy. And I think that problem already in your what is it? Bank soal bank soal. I think that question is already in your bank soal prosol prosol. So no surprise for that one. I hope you can do the question number 1 very well. Okay, so that's number 2. Number 2 is conceptually is easy, but sometimes maybe some of you will be very confused how to get C1 and 2 because you have limited time and it's a bit long mathematically. But conceptually I think nothing new from this one. Number 3 is a surprise. Okay, so that's why I choose to discuss about number 3 first. Okay, maybe you have question before we end this class. Okay, if you don't have question, this is our last meeting about the transport of momentum, about the momentum transport. Start from next week, we will move on to the energy transport. Okay, if you have no question, then let's finish this class and see you next week. Bye.